Alright, so today we'll look at some numerical integration methods, and this is just assuming that we haven't found the Riemann sum, or just working with an infinite amount of rectangles. Okay, so the numerical integration works a little bit like this. Before we look at the trapezoidal and Simpson's rules, let's look at the midpoint approximation. Okay, so what you do first is you find delta x, which would be the widths here. We talked about that last time. Okay, and how do we work with that? How do we find out what delta x? Well, you take b and you minus a, and then you divide that by n, which is the subintervals between a and b of equal width. Okay, so you just pick how many. In this case, we picked 4, so we would be dividing this by 4. All right, now that will give delta x. Okay, now what we're going to do is, instead of working with a lower bound or an upper bound, we would actually be working with the midpoint. So we would find the midpoint in each one of these sections. So this would be like x sub 1 divided by 2. This would be x sub 2 divided, well, not divided by 2, but it would be just halfway point between x1 and x2, halfway point between x2 and x3, halfway point between x3 and b, you know. Okay, so for each one, if you remember, each one's a rectangle. So if you take the delta x, which is the delta x would be the length right here, so it'd be delta x. Okay, alright, so delta x would be the length of each one. So it's this length right here. Okay, and then you times it by the height, and the height would be, what if we took the first midpoint and plugged it into the function? Okay, and then we added that with the length of the next one, which is going to be the same because they're all uniform, because remember, subintervals between a and b of equal width. Okay, and then we did the same thing. Well, if you notice, each one of these has a delta x, so we could factor out a delta x and just go, okay, delta x times the sum of the function of the first midpoint plus the function of the second midpoint plus the function of third plus the function of fourth. And we could just do it that way, and you would get the approximation. So that's how the midpoint works. Now, if you notice, we do have some overlap, like right here, here's some overlap, and here's some overlap here, and they're not exactly equal. So the next two methods are actually showing some interesting stuff. Okay, the trapezoidal rule is actually going to help reduce that a little bit. Right? And now sometimes trapezoidal rule reduces it, sometimes it doesn't. Now if you notice, each one of these is now a trapezoid. Okay, I'm still finding delta x this old way, b divided by a divided by n, or b minus a divided by n, except now I'm going to use the formula for the area of a trapezoid is height divided by 2 times base 1 plus base 2. Well, the height is now, if you turn your head on your side, the height is now this, and this is base 1, and this is base 2. So basically, it's going to be delta x divided by 2 times the function of x sub 0, which would be this length right here, plus this length right here, which would be the function of x plus 1, and then you add the other ones, and you just keep going. Okay, now if you notice, each one of them is going to have a delta x divided by 2, so we could factor that out, and we could just work with it that way. Okay, alright, so that's the trapezoidal rule. It's a little bit better, it's still not exact, and remember, this is still all approximations. Okay, now Simpson's rule actually will be, we will be using quadratics for this. Okay, now this one, I'm not going to go into depth as a proof and stuff, but in other ways, if you look right here, here's an actual approximation, and this is its own quadratic, this would be its own quadratic, this one would be its own quadratic, and it would just continue to work that way. Okay, delta x is still b minus a divided by n, but now it must be even for Simpson's rule because we're going to divide each section into 2 parts, so that's where we're going to have n be 2. Okay, alright. Now, shortcut, I'm not going to show you the long part of how we got delta x divided by 3, but it's just basically, here's how it goes. Here's the pattern. Okay, so the first term is the function of x sub 0, so it's just this length. And then we're going to add 4 times x sub 1. So for every odd x placement, we are going to times it by 4. So that's when it's odd. For every even placement, okay, each one of these, we're going to times them by 2. Okay, odd times 4, even times 2, odd times 4, even times 2. And once we get to the last term, we just leave it be. Okay, we don't times it by 4 or 3 or 2. Okay, but that's just basically how you do the Simpson's rule approximation, and this is how you get the correct quadratic approximation for each interval, or each couple of intervals. Okay, but that's basically it. Just make sure you practice looking at it, and definitely look up some examples. But here's just how the formulas work, and the reason why they have a delta x divided by something out in front is because it's times by each part. We might as well just bring it out front. Okay, that's it for numerical integration. I'll talk to you guys later. Have a great day. Bye.